If I can see the thumbs up. Okay, so now let's try recalling what we were doing last time. So last time we started talking about this idea that we want to test, let's say, a general linear hypothesis, like something like this in a linear regression, and we could write this, or we can write it as A times beta for a matrix A, and we saw that A in general is not unique, but we're hoping that A is full rank or full row rank in the sense that the rows are linearly independent. So we are working with independent constraints. For example, we translated this into 3 independent constraints. And we saw that we can do the, can actually do independent, like individual hypothesis tests on each one of these constraints. And then the idea would be that we can combine them using Benverone's correction. If I pronounce it correct. But we wanted to do something better, something more powerful. So we decided to try this idea that we'll fit the regression once without the constraints on beta, and once with constraints on beta. Here I'm calling it beta hat H naught, but sometimes I call it beta hat A, referring to this A. And we saw that this is equivalent, this restricted problem is equivalent to sort of solving the general, another linear regression, if we can write the constraints in this dual form, which we did, for example, in this case, by introducing this new parameter gamma, which was free, and then every beta in the constraint set would be like that, and then plug it into the regression model, and we sort of had this simpler regression. This is a different example, but once you plug it in, you get another restricted regression. You can solve this regression. You get a new beta hat, and then somehow we want to compare these two beta hats. And we saw that instead of doing that, we actually compare. We can compare the fitted values or the residual sum of squares, basically. So we had this geometric picture. Okay, let me mention this here. So these two hypotheses, you can state them in terms of the mu. Mu is x beta. So I can say that the if I define L of x to be the image of x, that's the Book's notation, I believe. It's the same thing. The set of all x betas such that beta is in RP plus 1. So our original regression model just restricts mu to be in this L of x. So regression model assumes mu in L of x. We can later test this also, but for now we assume that the regression model holds. We want to test within the regression model whether some more extra constraints also hold. And so instead of looking at the betas that satisfy the constraint, I'm going to look at x betas, where beta satisfies these constraints. This is equivalent to saying I'm looking at x beta such that beta is in the kernel of A. This defines a new subspace, and in fact, you can verify that this is a linear subspace, which I'll let you go and recall what a linear subspace is. And in fact, LA of x is a subset of L of x. It's really easy to see that. So the hypothesis test basically translates to something like that. Under the null, these constraints hold, so mu is in LA of x. Under the alternative, mu is not in LA of x, but it's still in L of x. So we would like to test that, and so we fit the original model without constraints, we get a mu hat. We fit the restricted model, we get a mu hat A, which is just x beta hat A. And then we want to compare the difference of these two. It's similar to the difference of beta hats or the residuals. So here's the idea again, the geometric idea. This is a little bit messy. Let me maybe let me clean this. This works. But I'll put this here. So what we are doing is we are fitting the regression model, original one, without any constraints. So that would correspond to projecting y onto L of x, just the image of x. So when I fit that regression, I get this mu hat, right? And then I get this residual, which is just the difference between y and mu hat. So we had this relation, y is mu hat plus e. And so you know that e is also orthogonal to the L of x. And you can see that I can compare, or okay, let me mention the other one. So the other subspace that we're working with, this is the subspace on which you assume mu lives under the null. So under the null, I know that mu is actually in that subspace. So instead of projecting onto the bigger subspace, I can just project onto, instead of projecting onto L of x, I'm just going to project onto LA of x. When I do that, I get a new vector, mu hat A, which, as you can see, it's not necessarily the same as mu hat. Then I can compare these two. So the way to compare them is to look at the size of this difference, mu hat minus mu hat A. But there's also this Pythagorean theorem, which is easy to prove, because, for example, you know that E of A is orthogonal to mu hat A. And we also know that E is orthogonal to both mu and mu hat and mu hat A. Okay. Actually, this one I don't need. YE is orthogonal to both mu hat and mu hat A. Why? Statement. E is orthogonal to the image of x. Yeah, and mu hat and mu hat A are both in the image of x. Mu hat is, by definition, mu hat A is in the, like, LA of x, which is a subset or subspace of image of x. So both are there. So this is true. From this, it follows that E is also orthogonal to mu hat minus mu hat A. Okay, orthogonality is this, like this. So if you're orthogonal to two vectors, then you're orthogonal to any linear combination. So this is a right angle. So if you look at this triangle, you can write a Pythagorean theorem, which is saying that the size of E squared plus the size of mu hat minus mu hat A squared is the size of EA squared. Okay, this is easy, or you can expand. Basically, EA is, you can see mu hat minus mu hat A plus E. From the picture, you can see that. And then I take the square, and we had a formula, x minus, this has like x squared plus y squared minus 2 inner product of x and y. So if x and y are orthogonal, so this would be x, this would be y, then you'd see the Pythagorean theorem. So this I ask you to do as an exercise. This is like a generalized form of these identities that you have. A minus b squared is a squared plus b squared minus 2. Okay, so comparing the size of, or how close mu hat is to mu hat A is equivalent to comparing the difference of these two. And you can also see that this guy is always going to be bigger than this guy. So the residual sum of squares for the restricted model is always So we see that this guy is always bigger than this. Why? Why is that? No, they're sort of both outside these. Yeah, one is restricted, one is not. So intuitively, the residual sum of squares for the restricted model has to be bigger because you have less freedom to fit. But can we argue it mathematically? Yeah. Yeah, so great. Great. Yeah, so that's the idea. So this is non-negative, this term. And so what you get is you had a, like at best is equal to this guy. Otherwise, it has to be bigger. I want to point out. Okay. Yeah, so yeah, this term is always non-negative. So I look at this, this is a best equal to this. But this is a little bit positive. It's not never negative. So, and this sort of intuitively is clear. So the restricted model is saying that the restricted model cannot fit as good as the larger model. The bigger the model, the better you fit to reduce the residuals. Yeah. Mu hat A and mu hat. So you're talking about basically this guy and this other guy. What do you guys think? Are they perpendicular? You can imagine moving this y around. They don't have to, yeah. But this mu hat could get very close to mu this, I can move to this side. You can imagine this like moving y. And so this angle is gonna get wider. Okay, this end could be very close to the end of that could be very close to this line. And so this would be like this. You can get anything. So these are vectors. There's no small or large. Norm, you mean? The what? The what? You're talking about this versus this? Yeah, I don't think there is there's a clear relation. Yeah. It could go either way. There's something else which is orthogonal. There's another orthogonal or right angle, maybe. You guys can point it out. There's another triangle with the right angle. There are two errors. Which one? We already have one, which is going to be the useful one for us, which is this guy, the right angle here. There's another one. Mu hat and no, this is the same story, but not. Mu hat and EA. You're getting close. Mu hat A and E, no. Yeah, the mu hat A and E are true. Yeah, so that's true, but they're not in a triangle. Yeah, what was that? Mu hat and E, yeah, so that's true. That's good. This is mu hat A and E, yeah, so that's the one that I was looking for. There are a lot of things, but this is a right triangle, triangle with a right angle. Why? Yeah, because you're projecting y onto the image. Whenever you project, the error would be orthogonal to the projection. Right? So this is the error of that projection, which we orthogonal to this guy. I'm not going to use this, but yeah, there are at least 3 triangles with right angles. Yeah. You guys focus on the one which is not. So none of these, but the other ones all have right angles. Okay, good. So you understand the geometry. So what I want to do is now, so basically how well the restricted model fits relative to the full model determines whether you want to reject or not. So if this restricted model is very close, that the residual is very close to the full model, it means that even with restrictions, I can fit well. So I'm going to go for the null hypothesis. If this is very far from this, it means that the full model is doing a much better job. And we probably assume that, or we can guess that the null is probably not true. So the easiest way to see, so any questions about this figure? So the easiest way to see is if you assume that the noise in the model, so there is this noise, y is mu plus epsilon. This is the random noise, basically. This is not a residual, right? This is what we don't observe. And this is what causing y to go outside this subspace, because mu, true mu, which I'm not showing here, is in this subspace. And what causes y to go outside is this randomness. So the easiest way to see what is going on is if I let this be 0. So in the ideal case, there is no noise. So y is equal to mu. That's the situation that we have here. No noise, y is equal to mu. So we have 2 cases. Under the alternative, mu is in L of x, but not in LA of x. So this is the situation that I'm demonstrating here. So y is equal to mu and is outside LA of x. Then I project y onto L of x, the bigger subspace. I get back y itself because it's already there. So mu hat would be equal to all of these guys. But when I project onto LA of x, I get something different because, well, this is outside that subspace. So there's going to be a proper error here. If mu is in LA of x, which then implies that mu is also in L of x, we're under the null. So that would be y, which is also equal to mu. Now, when I project onto both subspaces, I get back the same thing, which is y. Okay, because the y is in like the smallest of the 2, projections onto either one would be itself. So in this case, mu hat and mu hat A are going to be equal. Difference is 0. So based on the difference of mu hat minus mu hat A, you can tell these 2 perfectly apart. Now, when you have noise, so this is mu hat minus mu hat A. So this is strictly bigger than 0 here. This is equal to 0. So based on this or this square, we're just looking at the difference in size, or like the size of the difference, basically. We can tell the 2 places apart. When you have noise, however, you always have this often, unless your noise is very specific. You're going to have this bigger than 0. And so question is that how much bigger? How much bigger should it be before we reject? Does that make sense? So how should we questions? Online people, okay. So how do we determine this? Anyone remembers some idea? What we're going to do is actually, so equivalently, we're going to compare these two. So this squared is equal to the difference of this and this. So instead of looking at, we usually look at norm of EA squared minus norm of is equal. So these two are equal. So we compare the residual sum of squares. How do we do this? Yeah. Great. Right. Find the distribution. So these two are equivalent. So find the distribution of, let's say, this guy. And so let's say under the null, under H naught, and decide on a threshold based on, let's say, requiring a certain significance. So how do we determine the distribution of this? Anyone has any idea? Norm of E squared divided by, let's say, sigma squared. It's not T, it's something else. R squared with, yeah, this many degrees of freedom. That's true. I'm not wrong. This is a starting point, yeah. This is a great starting point. But this doesn't tell me the distribution of the difference. It's actually a hard question. I'm not expecting you guys to give me the right answer, but just maybe some ideas from these courses. Let's say if we want to figure out the distribution of this, like the standard approach is figure out like the joint distribution of a vector that has these two. I have the marginal distribution, but if I can recover the joint distribution of this, let's say, then this is a linear transformation of that vector. I can use rules of transformation of distribution. But even this would be like, a little bit difficult. I might be able to like compute the marginal distribution of this, something like that. But the joint is complicated because both of them rely on the same random vector. So they're sort of dependent. And things are not linear. So it's not like we have. So EA and E, I can find the joint distribution of this perhaps because they're going to be linear or affine functions of Y. So you have the technology to find the joint distribution of this. But this guy, this is a vector. This is like a 2x1 vector. This is like a very like 2n times 1 vector. So this is like summarizes that information in nonlinear fashion. So it's not that obvious. So we're going to determine the distribution of this, and it turns out that in this particular case, under the Gaussian assumption, this has a very nice distribution. And that's basically the same thing here. So the point is, I just wanted to point out that this is not a trivial task. We'll say that under this model, with the Gaussian assumption, the usual Gaussian assumption, if nu hat is the projection of y onto the L of x, something. And then mu hat a is the projection of L a of x onto y, then the difference, this or the thing that we're looking at, divided by sigma squared is going to have a chi squared with q degrees of freedom. Q is the number of constraints, basically. It's not a non-trivial result. And it turns out that, fortunately for us, this quantity, the same, I mean, with or without dividing by sigma squared, it doesn't matter. This is going to be independent of the residual sum of squares for the full model. So this result holds under the null, not under the alternative. And it's just a basic building block. So now I can sort of determine everything that I want. I have the distribution of this basically. We're going to prove this later. Require some more machinery that we don't have yet. But I now have the distribution of this guy. And hopefully I can set a threshold for a significance level. The problem is that the distribution is sort of dependent on sigma squared. So what we're saying is like EA squared divided or minus this is distributed like sigma squared chi squared q. I don't know sigma squared. It's the same situation as the regression. So how do we deal with this unknown sigma squared? Sorry? Yeah, how do we cancel it out? That's a different question, yeah. So maybe someone different wants to answer that question. So we have the distribution of this. So the point was, you want to reject the null based on the size of this or the same quantity. And for this, we need the distribution under the null. I'm giving you a theorem that tells you the distribution, but the distribution depends on the unknown parameter sigma squared. Unbiased estimator, yeah. So usually you want to divide. So a natural thing would be if I divide this guy by, let's say, s squared. So in general, if I divide it by sigma squared, you can see this is like the same way that we wrote this. It's divided by sigma squared has a distribution that does not depend on unknown parameters. So q is the number of constraints, independent constraints. I know q. So instead of doing sigma squared, I'm going to replace it with s squared, which is our unbiased estimator of sigma squared. But can I say that this is chi squared? No. Why? Why not? It is. Maybe want to elaborate why? Because this is some random quantity, right? And potentially dependent on this, potentially. Even if it's not dependent, I'm dividing by a random quantity. And whenever you divide by a random quantity, you change the distribution, the nonlinear transformation. In particular, this could be very small. And so you'd expect whenever you divide two random variables, your distribution gets heavier and tails, because it could like become large with higher probability. Right? So if you divide by something very close to 0, it's more likely that I would get larger values. So generally, these things would have heavier tails. that's the thought. So how do we determine the distribution of it? You can use this part. So this guy is, so what is a formula for S squared? It's the same, like unbiased estimator under the full model. Yeah, okay, that's the same estimate that we had. So this guy is independent of that, so this is okay. This is the same as this, so these two are the same. So this is independent of this. Okay. Yeah. I'm gonna put it here. They cancel out. If you think about it. Yeah. This one is like that. Yeah. So this is chi-squared with n minus p plus 1 degrees of freedom. This guy is chi-squared with q degrees of freedom. It's close, but it's not yet an F distribution. What is an F distribution? Yeah, so if I have a chi-squared divided by its degrees of freedom, and then another chi-squared, let's say with d degrees of freedom, divided by its degrees of freedom, then this would have an F distribution, assuming something. Assuming what? The ratio of any two chi-squared. So this could be exactly the same as this. They would cancel out, let's say. There would be no F. So what is the condition? Q is not what? No, it's like the same. So let's say this is a random variable. If you want to be a little more careful, let's say x is chi-squared with q degrees of freedom. Y is chi-squared with d degrees of freedom. Let me do this. D1 chi-squared with d1 degrees of freedom, chi-squared with d2 degrees of freedom. I'm going to divide this by its degrees of freedom, and then the other one by its degrees of freedom. I would like to claim that this has an F distribution. It's not going to be in general true. So x could be like exactly equal to y, d1 equal to d2, and this side would be just 1, like constant 1. Yeah, go ahead. Yes, okay, good. So if this and x is independent of y, this is true. Like a t distribution, you need the numerator and denominator to be independent. Without that, I can't even determine what the distribution of this is. It could be anything. It depends on the joint distribution x and y. So if you say that they're independent, you basically specify a unique joint distribution. So you have specified the marginals together with independence, you have a joint distribution. Then you can actually ask the question, what is the distribution of this? Which follows from the rules of transformations of distributions under transformations. And it turns out that it would be F. That's actually how it's defined. So what should we do here? I'm going to have to divide here. So instead of this, I'm going to divide this by Q. So there's going to be a Q here. And you'd see that everything works out. It would be like the chi-squared with q degrees of freedom divided by degrees of freedom, and the chi-squared with n minus p plus 1 degrees of freedom divided by degrees of freedom. So this, and the whole thing, so both the numerator and denominator are independent because of this. So numerator is like a function of this, deterministic function of this, and denominator is a deterministic function of this. And so the random variable which is on top is independent of what is on the bottom. So this whole thing is going to have an F distribution of q and p, like n minus 2 plus 1 degrees of freedom. So if you summarize, you get something like that. So this is what is called additional sum of squares, sometimes, or extra sum of squares. So the extra sum of squares, which is the difference of the two residual sum of squares, divided by its degrees of freedom. We didn't talk about degrees of freedom of this, but we'll see later that this has a meaning of degrees of freedom for this guy. And then this guy divided by its degrees of freedom, you can see that sigma squared cancel out. Okay? So these guys cancel out. What I'm writing here is basically this guy. This is turns out to be that, and so this has an F distribution. So the whole point was we determined the distribution of this difference, but there was a sigma squared, just like the t case. We have to somehow get rid of it. We can normalize by the estimated variance, but then we have to be a little bit careful because they're random. But this theorem that we had sort of is very useful because it says that the top and bottom are independent. And if we sort of adjust the degrees of freedom, like these Hughes property and minus p, if we normalize them properly, then their ratios would be an F. So this side does not depend on any unknown parameter. So this is under the null. So under the null, I know the distribution of this. I can use it as a test statistic. And intuitively, it's sort of very nice because it tells you that it's not just the absolute value of this that matters for testing. You have to somehow normalize it. How big is it? It is. You're going to measure it relative to how big this one is. So as a fraction of the size of the residual in the full model. You care about that, not just usually like in the statistics, like absolute deviations don't matter as much as like relative to some base. So the size of this in general would depend on how noisy your data is. You don't know ahead of time how noisy things are. So it doesn't make sense to just set an absolute threshold. It just doesn't depend on the noise. And this sort of, the noise is buried in there. So the larger the noise, the sigma squared, the larger this is, because you're seeing the size of this is sort of related to, after proper normalization, actually a good estimate of the size of the noise. So we divide basically by our estimate of the size of the noise, which is, that's the residual sum of squares. Okay? Any questions? Because of this theorem, which I'm sort of giving you without proof, but we'll prove it later. It follows from a result by Cochrane's theorem, which you're not going to prove, but hopefully by that point, you're more convinced that they're independent. It's not at all obvious. Okay. I give you that. We just have to, for now, accept this as a fact, and then later we hopefully prove it. Any other questions? Okay, any questions? So the only thing that we haven't proved yet is this. We'll prove this later. But if you agree to this, then the F follows. And this is again the result that I'm referring to. If you have two chi-squared with independent chi-squared, and then divide them, and then divide each one by the degrees of freedom, and then divide the resulting random variables, it's going to have an F distribution. So this guy is called additional or extra sum of squares. This has n minus p minus 1 degrees of freedom. This is like the degrees of freedom of the chi-squared. This has q degrees of freedom. This is the corresponding degrees of freedom of the chi-squared. And then you can associate a number of degrees of freedom to this. which is just going to be n minus how many parameters are in that restricted model. And if you recall, the number of parameters in the restricted model is p plus 1 minus q, because we have q constraints to eliminate 2 degrees of freedom. So this is the degrees of freedom of basically beta in the restricted model. And so this n minus this would be the degrees of freedom of the Israel solid square. So the degrees of freedom, this is just the degrees of freedom of a solid squares in any regression. It depends on how many samples you have and how many effective parameters, number of effective parameters or free parameters. Which is, the degrees of freedom of this is a little bit tricky, or like that doesn't look like a residual sum of squares, but for now, let's call this degrees of freedom q, because it's just actually chi squared with q degrees of freedom. We're going to talk more about this idea of degrees of freedom, but they add up. So if you add this and this, you get degrees of freedom with this. Everything sort of adds up. So no degrees of freedom is lost in this process. And basically, the degrees of freedom are useful for constructing these test statistics, because they are the degrees of freedom of the corresponding chi-squares. So we can perform this. How do we find mu hat A? Just you fit the restricted model. And how do I set a threshold? So I'm gonna, so like my test would be like, we call y and x would be like, we're gonna say alternative is true if f hat is bigger than some threshold. Otherwise, it's going to be the null. And the way I'm going to determine the threshold is that I'm going to, under the null, try to set this equal to alpha. That would be the type 1 error. This is the type 1 error. Probability of rejection under the null. And I can determine this tau, or you can determine the p-value similar to what we did. So everything works out, except that instead of a t statistic, now we have an f statistic. But we have the distribution, that everything sort of goes as before. Okay? So once you have a statistic based on which you're building your test, and you know the distribution under the null, you can set the threshold to have a certain value or size or significance level. These are all the same. Thanks. Questions? Yeah. Can you speak up a little bit? Q is the number. Yeah. So anyone remembers what Q was? Yeah. So the number of independent constraints, if you recall. Yeah, Q is like the number of rows here. So this is a matrix Q by P plus 1. And I could like add more restrictions, but there's if I want linearly independent restrictions, the number is the same, no matter how you write this A. So for this, for example, no matter, like these are two different representations, you can see the number of independent rows is 3. So there are 3 constraints here, independent linear constraints, and that's key. So we like went over this idea of the number of constraints and how like, we eliminate. So the number of free parameters in the restricted model, you can see is p plus 1 minus q. Once you eliminate, like in the dual, this b would be p plus 1 times and this gamma would have this many free parameters. So that's like the degrees of freedom of basically the restricted model. And there is residual sum of squares in that model. So just review these slides or the lecture. We talked a lot about what happens to these degrees of freedom once you do the restriction. From a linear algebraic point of view, these are all just dimensions of different subspaces. Once you impose constraints, your linear subspace loses dimensions. So basically, You start from a linear subspace, you impose one linear constraint, the resulting subspace is another linear subspace, but with dimension 1 less. You impose 2 constraints to reduce the dimension further. Question? Let's see an example. It becomes more clear. So we have this model. This is from your book. This is like an experiment, I believe. Maybe it's like real. Let's say you have 5 drugs, oral receptors, and they are. You want to like see the effects on blood cholesterol level. So HDL, good cholesterol. So you give them to 2 groups of people. Actually, you have 5 drugs, five versions of this drug, or 5 different drugs, and you divide your you like have a bunch of people volunteer to do the experiment, and then you divide them into 5 groups, and you give each one of the drugs. And what you do is that you measure their cholesterol level before and after giving the drug. So before, it's called Z. So we have a variable which is the initial cholesterol level, and then after they had the drug, let's say after some time, you measure the final later cholesterol. So this is the initial, this is the final cholesterol level. And so you'd guess that the initial, so the final cholesterol level is related to the initial level. Some people have higher like baseline cholesterol level. So there's going to be a factor here that determines the relation of this, maybe linearly related to the initial cholesterol level. But the drug also has an effect, and you want to determine that effect. So you model it as this regression. So these xi's, like x1 up to x5, these are indicator variables. So x1 tells you, so xj basically, it's 0 or 1. If it's 0, it means that you didn't take that particular drug, the J drug. If it's 1, you took the J drug. So for every one, you have some yi, and you have some zi, some initial cholesterol level, plus one of these variables is active. So beta 1, let's say xi1, beta 2, xi2, that's beta 5, xi5, plus epsilon I. Out of these, only one of the terms is there. Let's say if I took drug 2, this would be 1, the other ones would be 0. So my sort of final cholesterol level is alpha z I plus beta 2, basically. So beta 2 is like the addition provided by that drug. So you're assuming that just provides some shift, okay, so positive or negative. Whatever your initial cholesterol level was gets multiplied by some factor plus the effect of the drug that produces your final output. That's sort of the modeling assumption. It's like a constant, each drug produces a constant shift in the level of cholesterol. Could be positive or negative, but it's the same for everyone who took that drug. This encoding of this, like the indicator business, is really useful in trying to encode everything into one regression. Okay, so so let's say the ith guy took the ith drug, so let's say xi2 was 1, the rest are 0, so this would be beta 2. Let's say the kth guy, or let's say the kth guy is like another guy. They took the third drug, so this would be 1. For them, the observation would be alpha zk plus beta 3. Okay. So their xk3 is 1, the rest are 0. So once you write this down, it's just like you have y1 up to yn, and then alpha z1 up to zn, and then I'd have beta 1. Let's say all the people that took drug 1, I'm going to like order them to be like index from 1 to, let's say, n1. They come first. So for all of them, the first, like the x would be like 1 here. Let's say up to n1, and then the rest is 0. All the other guys, so these guys would have 0 on all the other drugs. Okay. The second group will have like 1s here, 0 elsewhere. And so, and then the last group will just have 1s here and 0 elsewhere. So if you look at each row of this, I shouldn't sort of intersect. Each row just has each particular row. For example, look at this row. Exactly one of these vectors is 1, the rest is 0. Like one of those coordinates is 1, the rest is 0. So this is the structure of the model. So it's like having multiple groups. So you probably have seen it in previous courses, like without the initial, probably this guy. So you can just do like an F-test, ANOVA, determine whether the drugs are the same. So they have this grouping, that your variable is just grouping, but you can write it as a regression. So it's just, once you write it as a regression, you can also throw in other information, like the initial level, which is not obvious if you just have the grouping variable. But the way that we model this is important. So I write a regression based on the information, and hopefully this makes sense. Once we agree that this is a good model, then we can apply our results. So we have modeled something like that. So the point is, yeah, the errors would be like this as well. So if you agree about this model, then you can talk about the rest. But writing this is part of the soft skills, so it might not be obvious how to do it. Some experience probably becomes a little bit easier. It might not be a good model. But, you just have to understand what you're doing. So what you're saying is that each person, the cholesterol is like a linear function of the initial value plus a constant shift introduced by the drug. And that constant shift is the same for everyone who took that drug. So that's really beta 1, for example, for drug 1. That gets like added to the value of the final cholesterol level for all these guys. Beta 2 gets added for all the other guys in group 2 and so on. So the effect of drugs are constant shift. Does this make sense? Even if this wasn't there, I could like write a regression like this. This is saying that there is a like constant mean effect. So there is a noise. It's not like, so if you imagine like yi would be like alpha zi1, let's say for the guy that took drug beta 2, plus it's going to have a noise. So I didn't include the noise here. It's not going to be exactly beta 2. That would be very too easy. It's like fluctuates around beta 2, but there's a constant level. Okay. So this is basically, you can think of this as the effect of the drug. There's some noise there. But there is like a baseline, there is a mean. So the effect that we care about, the mean effect, okay? The mean effect of the drug, which is going to be beta 2. Does it make sense? So these are dummy, sometimes called dummy covariates or indicator variables. We take only zeros and ones, and we constructed them ourselves. It's not like like weight or height or something that you observe. It's just you assign them to groups, and now I can encode that information as an indicator covariate. You can throw into the regression as well. So now I have one continuous covariate and these indicator dummy covariates. 5 of them. But now this is a perfect regression model, perfectly fine regression model. You don't care about the structure of the covariates, just I have 6 covariates. There's no intercept because we didn't sort of need it in this model. You could encode these groups differently. There are some slides later or in your book that I talk about that, whether we go over them or not. So you could, for example, take the effect of drug 1 as the baseline, and then model the difference of drug 2 and drug 1. So that would give you a different regression. But the results should be the same. So this formulation is good if you want to set, let's say, test whether the drugs are all have equal effect. Because the betas are the effect of different drugs, then the test that I want to do is test whether they have the same effect. I can test this null hypothesis. Okay. The null hypothesis that beta 1 is equal to beta 2 equal to beta 5. That would be the test that tests whether they have the same effect. This might be something that you're interested in doing. Does that make sense? So I can write this. This is similar to what we did. This is one-way version of writing the A. I put zeros here because the alpha doesn't enter into the constraints. Constraints are about beta, so this whole thing is my beta vector. Then you have 1 here and then -1. So this encodes the first equation is telling you like beta 1 minus beta 2 is 0. The second equation is beta 2 minus beta, or sorry, beta 1 minus beta 2 equal to 0, and so on. And you can see there are 4 constraints. Once I have 4, then all of the 5 have to be equal. This is similar to what we did last time. And they're linearly independent. Everyone sees that these are, so this matrix is full rank. That's low rank. The way to do is like form a linear combination of columns, set it equal to rows, and set it equal to 0, argue that the coefficients have to be 0. They have to be 0 because each one is like almost 0 everywhere except one coordinate besides this. And so it forces. So the rank is 4, or like Q is 4. The number of independent constraints is 4. Yeah. I didn't get that. So can you speak a little? Smaller rank? What do you mean by smaller? So yeah, the rank just depends on your constraints, right? So we have 6 variables, and I have these constraints on these variables. So you have these constraints correspond to 4 linear independent constraints. If you have fewer constraints, then you have fewer of these, and then the rank would be smaller. Was that the question? So let's say if my constraint was just beta 1 equal beta 2 equal beta 3, I just want to test whether the first 3 drugs have the same effect, then I would just have this part. Okay. No problem. It just depends on what your constraints are. Okay, any other questions? So far so good. The sample size is also 50. And generally you would like Q to be less than or equal to the number of parameters in the full model, which is true. So everything is okay so far. So how do we do the test? We perform regression twice, once on the full model. Once on the restricted model. So for the restricted model, what I can do is I can set all of them equal to gamma. If I set all of them equal to gamma, then this would just give me gamma times x1 plus x5. This would be like gamma times a new covariance. And then I have another alpha z. So the restricted model. So the full model is like usual regression. For the restricted model, we have I'm gonna do that dual sort of approach. I said all of them equal to gamma. Then my model was like y equal alpha z plus all the other betas are the same. I factor out gamma and get x1 plus x2 plus x3 up to x5. X2, x3 plus x4 plus x5 plus the noise. So this would be a new covariate associated with this parameter, and then this is another covariate associated with this. So this is like a regression with two parameters. And you can see like p plus 1 was, let's not call it p plus 1 because there is no, let's call this d instead of p plus 1. That's the original number of parameters. So d was 6, q was 4, d minus q is 2. And you can see that's exactly the number of parameters that we have in the restricted model. So now what is this summation of these covariates in this case? You look at the structure of this here. I'm basically adding these vectors up. Yes. What is this equal to? The sum of these covariate vectors. x1 plus x2 plus. Yeah, exactly. So this would be just the vector of all ones, which we usually write it as 1n. Just 1, 1, 1, all the way 1. The reason is like for each row, you have exactly one in one of these, and the rest are 0. So when you add up, you get the 1. It's the same. So that 1 would be different in a different vector each time, but it's there. So this for each row, exactly one of these guys is going to be 1. The rest is going to be 0. Yeah, because they take one of the drugs. In an experiment, you might be able to combine them, but here just we assume that we had given each person one of the drugs. So this is a simple regression, basically. You get alpha z plus gamma 1n. This looks like an intercept, basically. Gamma. This is a simple regression with an intercept. Doesn't matter from the theoretical perspective. It's just another covariate. So you fit this. You get EA, the residual for this model, and you also had E for the original model, and you have everything else. So that's what happens. So now I'm doing sort of some notation. So I'm calling this new model M1. So that's the restricted model. Later on, I might use this notation. So this is a new model. It's a restricted model. I'm using the E sub M1 for the instead of E sub A. This is a better notation. So this is the residual sum of squares for this after we fit the model. You don't have the data here, but it's in your book. You can do it. And then I also do the SS. This is called also SSE, the residual sum of squares, RSS or SSE, called sum of squares error of error. We'll get to this again. So this is E squared. This is for the full model. You get this, and you can see this is bigger than this, which is what we expect. So the restricted model has a higher residual sum of squares, and this extra sum of squares would be the difference of the two. This is another test for you. If this turns out to be negative, you did something wrong, or there's something wrong in your assumptions or calculation. This should be bigger. So it turns out to be 427. So that's the question. Is 427 big enough to reject? We don't know a priori, but I can compare it to the size of basically this. So this, basically that's the F idea. So this sort of encodes the base error level. So if I divide it by degrees of freedom, it's a measure of an unbiased estimate of the noise. So we're going to do that. So I'm going to divide this by its degrees of freedom, which is 4. That's Q. And this guy, this guy, divided by its degrees of freedom, which is, this should be D basically, N minus D, which is 50 minus there were 6 parameters. There's no intercept, so that would be 44. So this divided by that, I get 1.87. That's the value of the statistic, and we know that this is in general distributed like an F under the null with 4 and 44 degrees of freedom. So then you can compute the p-value. Turns out to be 0.13. It's bigger than the usual 0.05, so we don't reject. So this part I hope people understand well. So the basically F is not big enough for us to reject the null at level 0.05. And so although M like has a better residual sum square, is a better fit, but this difference is not big enough for us to favor the complex model. So we pick the M1. So you can think of the F as like comparing the two models. This is the full model, M, with this residual. This is the restricted model with this residual sum of squares, and F gives you a very concrete way of comparing these two models. So we're going to go in favor of the simpler model, where all the drugs have the same effect. So we're going to. Let me just quickly mention that you could test, for example, another hypothesis, which tests whether any of these drugs have any effect. So once we know that they're sort of all equal, we can test whether all of them are equal to 0 or not. So that would be a new hypothesis. This you can encode as if I just add another constraint. So let's say beta phi is equal to 0 to the original set of constraints. So I get 5 constraints. So if I, for example, add 0, 0, 0, 0, 0, 1 here, and then another 0 here, it forces beta 5 to be 0, and all the others are equal to this, so everything would be 0. You can see that that new set of constraints is like a set of 5 linearly independent constraints. So we have one more constraint. Effectively, the gamma, basically, gamma here would be 0. We set gamma. So the new restricted model is just this model. Let's call this M2. M2 is even simpler than M1. M2 is basically a submodel of M1. So this is a further restriction on M1, actually. So we have the full model, M1, which is a submodel of this, and then M2, which is a further submodel. Now I fit this model, I get this residual sum of squares, which is pretty big. The difference with the full model would be that. And then I divide this by the degrees of freedom, which is 5, because we have 5 constraints now. And this side is the same as before. I'm comparing it to the full model. And this turns out to be big, quite big, and then the value is 0.02. So we reject this. So we reject M2 in favor of M. So what happened here is that I compared these two via F. I didn't reject M1. So I compared the two as stick with M1. If I compared the two, that was the first F test that we did. Then we compared these two via an F test. That's the basically the idea that we were trying to do. And we did reject M2. So M2 is rejected in favor of M. In comparison of the two, I'm going to go with M1. So everything points to M1. Okay. So I compare these two, I pick M because I rejected the null. I compared these two, I didn't reject the null, so I picked this. So it seems like M1 is a good model after these. So the drugs have the same effect, but that effect is not 0. So if you think of this, I can come back later and talk about this. So think of this procedure of the linear hypothesis as comparing models. Or this F test, it gives you a lot of perspective. A lot of things that you do in lower division classes are basically doing this comparison. Even the t-test is a version of this. You can write it equivalently as an F test. Okay, questions? Okay, thank you guys. I'm gonna come back to another round of this next time. It was a little quick. See you on Thursday. Okay, online people, thank you. Bye-bye. You don't have the name? No, but